I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover attack surface analysis, model analysis. This diagram shows the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training, and additionally, that you've completed the requirements taxonomy, security requirements, secure design principles, apply secure design, and threat prioritization plan trainings. Additionally, you should have completed the attack surface analysis, overview, and model creation trainings. This training will cover attack surface analysis, model analysis. Before getting into attack surface analysis, model analysis, let's briefly review where it fits in the overall attack surface analysis process. Here's the attack surface analysis process, which we previously covered in the attack surface analysis overview training. Our focus on this training is going to be on the second activity, that of performing the analysis. Within the analysis activity, the ASA SME takes the instrumented element model and performs an attack surface analysis, generating a list of threat candidates. To review, when we're performing an attack surface analysis, we're constraining ourselves to a particular element, which is an arbitrary subdivision of the system. Within that context, we're thinking about three distinct types of entities. And these are ports, protocols, and processes. And that's it. That's all we need when we're dealing with an attack surface analysis. Now let's look at an example system and see how it decomposes. Once again, here's the block view of our example system. We have the system and the entity that's interacting with it. We've got the processes, interactors, data being used, and data flows going between the various entities. With the attack surface analysis, we only care about the three entity types that we've just discussed. Let's consider how that reduction occurs. Here's the block view reduced to only the entities of interest, those being the ports, protocols, and processes. There are only a few things that we need to consider, and this is good because it makes our analysis much easier. As we can see here, we have the web server, core service, and console interface as the processes we care about. We have data flows going between the various entities. We have indications of what the ports that we care about are. From here, we can extract the information that we need. Now, let's look at the analysis process. The analysis that we perform will be based on taking the entities and subjecting them to a series of questions. These will determine whether or not the entity is properly constrained. The questions that we cover will make the term properly constrained fairly obvious. Let's look at each of the entity types and the corresponding questions we're going to pose to each of them. When considering physical ports, we start with what is probably the most obvious question: is the port used? This is the easiest question to be able to answer, and you should have the information that you need here in the model that's been created. Either this particular hole in the box serves a purpose toward the functional requirements, or it doesn't. Our next question is whether the port is required for the core functionality of the element. Now, this question is one which is useful in a safety-critical system because it informs whether or not the port is going to be impacted if there's a need to degrade the operation of the system. If something is not necessary for the core functionality, then it can be disabled. This is, strictly speaking, not a necessary question in order to constrain a particular port, but it does inform other aspects of cybersecurity. Our next question is whether the port is only required during development. This is an important question because during development, there are going to be needs that the development team has with respect to an element, or the system in general, allowing it to be able to peer into the box. And so there will, in all likelihood, be extraneous ports that are used for this purpose. In production, these ports should not be there because development has ceased and production equipment is minimized to what is necessary. Similarly, we can ask whether the port is required for diagnostics. Now, there's a fine line between the needs of development and those of diagnostics post-development. Generally speaking, from a cybersecurity perspective, we wish to make it impossible for entities other than those authorized to access this type of data. And so, we want to make sure that if you need to do diagnostics, there are controls in place that don't provide access to those who should not have it. Next is the question of whether the port is only required for deployment. And by this we include provisioning, update, and decommissioning. This is important because there are some systems where provisioning and update are done in a highly controlled environment, and others where they will be done remotely. As with diagnostics, it's desirable to not have things exposed that don't need to be exposed. Which leads us to the next question, is the port removable? Is there the capability of having a port that can be removed and, when necessary, attached? If you have an unnecessary port, is it possible to remove the physical interface connector from the system or simply not populate it? Should it be necessary for diagnostics or deployment at a later date, it can be added at that time. When it's not there, a physical barrier should be installed over the hole in the enclosure. And that takes care of our physical port questions. As a side note, it's important to keep in mind that there's a distinction between product cybersecurity and physical security. With physical security, we're talking about things like locks, covers, and tamper-evident seals. These are outside the scope of the product cybersecurity attack surface analysis, and therefore outside of our consideration here. If any of these concerns intersect with this analysis, they should be recorded in the appropriate risk register and communicated to those responsible for such issues. We consider the logical ports and protocols collectively. We're going to start with the same question we asked regarding the physical ports. Is the port used? Unlike physical ports where you can just take a picture of the element and see that a hole exists in its enclosure, when it comes to logical ports, you have to be told that a logical port is being used. You can't simply scan the system to see if a port exists because a port is a construct, and it can be spun up and torn down the same way that you would with a file channel. Additionally, since the attack surface analysis is a design activity, there's no software to scan. Next, the question that we have is the port number appropriate? This can be a difficult area to communicate since logical ports are just constructs, and they can be assigned any value programmatically. Many developers simply pick a number that's convenient for them. However, the use and assignment of logical port numbers is governed by the IANA. It's important that we not use a port which is registered for another purpose, because firewall, port, and protocol checkers are going to flag these as invalid communication. Additionally, the IANA only allocates one port to an organization and expects that port multiplexing will be used when multiple protocols are employed. Our next question is similar to our first set, and that's, is the protocol required for the core functionality of the element? This becomes important again in a degraded system when we have contention over the media that the communications is taking place. If you have a situation where you have contention, the highest priority traffic needs to go through, and you need to shed any other functionality, at least temporarily. Our next question, is the port only required for development? Consider the example where you have a sensor that has a web server on it because that was the easiest way to move data around and examine things. In production, you shouldn't need that port. Next, is it being used for diagnostics? If it is, then that means when you're dealing with diagnostics, there are additional checks that you should be making. Similarly, is the port only required for deployment? There's no point in having a port listener running if you don't have active provisioning or update in process. Next, is the port owned by a single process? This is one of those issues where a resource should only be managed by a single process, so that we don't have issues of contention that come up. Additionally, if you know that the port is only managed by a single process, then you limit the chances that a rogue process will be able to open that particular port. Next, is the port only open for the duration of the required operation? This is one of those pressures on the system and attack opportunity issues. If you don't need a port open, don't leave the port open. This would be akin to having a global variable that happens to have a password in it because it's easier than fetching it from a password manager when you actually need it. Keep in mind that a port listener takes up CPU cycles and responds to queries. There's a whole host of things that can go wrong with this. Finally, does the protocol require non-trivial authentication? This is especially important when we're talking about things like diagnostics and deployment. Having a port listener sitting there waiting for a command it will simply execute is not the way to have a secure system. For information about what's meant by non-trivial authentication, the best place to look is going to be in the NIST SP 800-63 Digital Identity Guidelines document collection. And as a reminder, references with links are provided at the end of the presentation and in the video description. This brings us to our third group of entities, that being the processes. Unsurprisingly, we're going to start out with the question, is the process used? If it's not, then it shouldn't be there. Our next question is the process required for the core operation of the element? We've already discussed the concept of degraded operation, and so I won't belabor that here. Is the process required during development? Is the process only used for diagnostics? Is it only for provisioning? Now we have a new question. Does the process have a unique owner? This is where we again talk about a resource being managed by a single owner. Why? Because one of the controls that we can use to ensure cybersecurity is the access control mechanism provided by the operating environment. If a process has a particular owner and only they can start the process, then you don't have to worry about the process being co-opted by a different user or entity. A similar question is whether the process is required to be privileged. This is a matter of least privilege. Finally, is the process the manager of a system-critical resource? This is one of those questions which will guide us to knowing how strictly we need to apply the security controls at our disposal. With all these questions in mind, let's turn our attention to the example we've been using and see what we can come up with. Here we have the physical enclosure for the element that we're considering. We've taken that and created a simplified view of it. Now let's look at the results of the model creation and apply our physical port questions. Here we have the physical ports list from the attack surface analysis model creation activity. If we start out with our first question, is the port used? We can see that ESC 5, 6, 9, 10, 11, and 13 are not used. So those are obviously things that we would like to have removed from the element. Our next question is the port required for the core functionality of the element. We don't have anything that would indicate that anything is not used for the core functionality because we can see that ESC3, our normal operation data traffic, is the only core functionality that we have. Is the port only used for development? We've got examples of that with ESC1 and 2, which are our mouse and keyboard. We have ESC4, which is for development, but it's not noted that it's for development only. So there's ambiguity there as to whether we're using it for development and diagnostics or just for development. That's something that should be clarified. We have ESC8, our VGA connector, which is probably a display to go along with the keyboard and mouse when we're doing development. And we have ESC12, which is our second Ethernet interface. When we're looking at things which are development only or for development and diagnostics, then we should come back to them when we're doing the attack surface analysis review. Our next question is the port used for diagnostics? Again, we have the question as to whether ESC4 fits into this category. Because it's a USB port, it could be. Next, is the port required for deployment? As we can see, we have ESC7, a serial interface which is used for system configuration. Finally, is the port removable? For this, we go back to the photograph of the element and we can see whether any ports of interest might be removable. Next, we'll look at our logical ports and protocols. As we can see here, this is our block diagram stripped down to show our two interfaces. One is an Ethernet interface and the other a serial interface. So let's look at those. When we look at our logical ports and protocols list, we can immediately see that the serial port isn't listed here. We can look at this in one of two ways. The first is that it's been forgotten and you're going to have to go and add an ESL2. The other is that this is an RS-232 serial interface which has already been defined as being used for configuration. The fact that it is a required interface and that we know that it's an RS-232 interface implies that there's no logical port associated with it. And so there's no necessity to include it. But you're free to include it if you want to take the view that all of the things need to be listed. Setting that aside, let's look at what we have here. Our first question is the port used? Yes, this is defined as communication to and from the web server. Next question, is the port number appropriate? We look at our protocol and see that it's HTTP. We look at our port number and see that it's 6249. We know immediately that this port number is not appropriate for this protocol. The port the HTTP traffic should be on is port 80. Now, this is different from the question of, is the protocol correct? And we'll get to that. So we have an issue with the port number. Next, is the port required for core functionality? Yes, it is. It's our communication to the web server. Is it required during development? Since it's a core functionality, this isn't relevant. It's not just for diagnostics. It's not used for deployment. We don't actually deal with provisioning in this element. Is the port owned by a single process? We don't know. That would be something defined in the requirement, in this case ESR3. Is the port open only for the duration of the required operation? Again, we don't know, and we can explore that during the attack surface analysis review. Finally, does the protocol running on the port require non-trivial authentication? And here we get into the question of whether this is the appropriate protocol to be using. If we were to use HTTPS, then we'd have the ability to say, yes, we're not using trivial authentication here, but since we're using HTTP, there's no authentication. This is an example of why you look at the logical port and protocol in combination. Here's our block diagram showing just the elements processes. We have the core service, web server, and console interface. Let's look at these and answer some questions. Unlike the list of logical ports and protocols, here the processes are completely enumerated. Our first question is the process used? In this case, yes, all of these processes are required. As to whether the processes are core to the operation of the element, that becomes a discussion point when you're talking about the console interface, but for ESP1 and 3, the core service and web server, those are integral to the operation of the element. Are any of the processes used only during development? The answer for that is no. These are all production processes. None of these processes are only required for diagnostics. As to whether a process has a unique owner, this is an interesting question that we can't identify at this point based on the information that we have in the design phase. It's going to be available to us when we're doing the attack surface analysis review in the verification phase. Is the process required to be privileged? Again, this may not be well defined at this point. Is the process used for deployment? Within the context of what we know about this particular element, we can't say. And finally, is the process a manager of a system-critical resource? Both the console interface and the core service are managing resources which are critical to the system. In later activities, we'll use this information. Now let's consider what we do with the issues that we've just identified. For all of the potential concerns that we have within the context of this example, not everything rises to the level of being an issue. To understand that better, let's look at a categorization that takes all of the ports, protocols, and processes and puts them into buckets. From that, we'll be able to see which of the things that we have concerns with really need to be addressed as issues. First, we have things which are required. These fall into two subcategories. They can either be core, the system will not function without it, or, by extension, there are things which are supporting. The required category gets a pass regardless of the subcategory. These are things that we have to have and that should be there. We're taking note of what's core and what's supporting because if we have to put the system into a degraded state, we need to know what those entities are. Next, we have those things which are required for deployment, and by this we mean provisioning, update, and decommissioning. These are obviously required, but temporally contextual. They don't need to be active all the time, nor should they be from the perspective of pressure on the system. Next, we have those things which are for development. Taking into consideration the fact that we're doing an attack surface analysis in the design phase, we can't speak to the eventual disposition of these concerns. We know that they're being used now, but by the time that we get to the verification phase, they should no longer be in use. So this is informational at this juncture. We'll get to the verification phase and do an attack surface analysis review, then ask whether these have been turned off. Finally, we get to the area where we have concerns that will need to be addressed. The first is that of diagnostics. These should not be active continuously. We should not have exposure for diagnostic ports on the physical surface of the element. This gets us to the question of, do we have things that are physical interfaces which can be removed? And do we have adequate controls in order to prevent the diagnostics which tend to have more intrusive access into things than we would like from being misused? Next are things which are simply unjustified. They're either out of specification, for instance, the issue identified with the logical ports and protocols, or there's no underlying requirement to justify their presence. For instance, you've got a web server running on a sensor, and there's no reason for the web server to be there. It's not required for the functionality. And finally, we have those things which are unused. These last three categories are the ones that we need to raise as issues. The rest are informational, but may have use in later cybersecurity activities. With all this in mind, we can compile our list of identified issues that we're going to need to dispatch. The AVCDL document, Attack Surface Analysis Procedure, details the various issue types and issue reasons, which is noted in the categorization section, are things like debug only, out of specification, and unused. The issue types listed in the analysis document go beyond the scope of what we've discussed here because the approach that's being used is determined by the fact that we are in the design phase. So we're going to have issue types that we don't have visibility into. When we get to the attack surface analysis review, we will have a complete system and element, and at that point, we'll be able to address these things. But at this point, some of the issue types won't be applicable. We've covered ports, protocols, features, and diagnostics, but data connection lifetimes and data structures are not going to be able to be addressed here. They're included for completeness. Once we have our identified issues, they can be fed into the triage activity. With that, we've covered the analysis activity we use for the attack surface analysis process. Now let's look at some takeaways. First, review the model. Whenever you're doing any type of analysis, look over the model to see if it's coherent. As you're proceeding with the analysis, if there's any information that's missing, then go back to the model documentation and query the development SME involved in the creation of the model. Next, focus on the information provided. This goes along with the first item. Don't make assumptions about the element. Always work from the information that you actually have. Although we won't generate issues that need to be addressed right now, the development and deployment aspects are going to require production plans, and development should be reminded of this. They should know that this is the case, but it never hurts to remind development that something is going to be needed to be in place to address these issues. And obviously, when we do the attack surface analysis review, we'll come back and look at these more stringently. Next, keep the analysis up to date. If the element changes, then the attack surface analysis also is subject to change. And finally, keep in mind that you don't require any special tooling to do this type of analysis. The set of questions and the methodology both lend themselves to a purely pen and paper exercise. For additional information and to get a more in-depth set of references, the attack surface analysis procedure tertiary document is available in the AVCDL GitHub repository. The materials used to cover this example are in the location shown here. All AVCDL materials, both in source and distribution forms, are available on our GitHub site, as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. A set of training videos has been created to cover various aspects of the AVCDL that follow the training path found in the AVCDL primary document. It's important to note that all AVCDL materials, except for the introductory blog posts, are intended for product cybersecurity engineering practitioners. With this training complete, once you've completed the other trainings related to attack surface analysis, you can proceed to one of the other trainings at this level. These include threat modeling, penetration testing, and vulnerability identification. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation source material will be provided on the AVCDL GitHub repository.